Hello and welcome. Today we will hear from Jordan Mullikin and Divya Rupini Amarthaluri, both students at George Mason University, as well as Stephen Burmeister, an assistant professor at George Mason University. They will be discussing forensic use of GPR and LiDAR technology for clandestine grave detection. So, without any further delay, I will turn things over to our presenters.
Hello, everyone. My name is Jordan Mullikin, and I will be our first speaker today. It is my pleasure to introduce our topic, which is the forensic use of GPR and LiDAR technology for clandestine grave detection. So this research would not have been possible without the funding and assistance and support from the National Institute of Justice, specifically their Forensic Technology Center of Excellence, as well as the Research Triangle Institute. As it was just mentioned, this was conducted at George Mason University via members of our forensic science program. So we have three learning objectives for today. So we will start by hearing about the function and use of ground penetrating radar to detect clandestine grave sites. That is what I will be discussing. And then I will pass it over to my colleague, Divya Rupini Amarthaluri, who will discuss the function and use of light detection and ranging, or LiDAR technology, to detect clandestine grave sites. And lastly, our supervisor, Stephen Burmeister, will discuss the potential for data integration between GPR and LiDAR to advance the detection of clandestine grave sites. So what is GPR? Ground penetrating radar, or GPR instrumentation, utilizes radio waves to reveal subsurface information such as the depth of scanning medium, the compositions of the scanning substrate, and hidden objects or voids. So what is happening when you're using this instrumentation is it is sending waves into the ground, and those waves travel at different rates depending on the substance that they're hitting. So based on the difference in the rate that the waves travel, analysts can utilize scanning results to locate targets such as clandestine graves. So for the remainder of this presentation, we will be focusing on geophysical instruments, but I do want to introduce you all to the two broad categories of GPR instrumentation, which is geophysical instruments and handheld instruments. So geophysical machines are instruments that are very large, and they're either pushed or pulled along a surface. So these are used for larger targets and have historically been used for the detection of utilities, archaeological remains, and forensic uses such as the detection of unmarked graves. However, there are smaller handheld instruments that can be used along the ground or walls. So these are used for smaller targets, such as the detection of items hidden within walls, such as narcotics or rebar. I once worked with an archaeologist who used handheld instrumentation to find smaller bone fragments at archaeological sites. But for larger targets, such as unmarked graves, you would use a geophysical machine. So for our research specifically, we used the Sensors and Software LMX200 Enhanced GPR system. So this is advertised for utility locating purposes, but the frequency, 250 megahertz, allows for the use or application of forensic and archaeological investigations as well. So this can be applied to collect multiple types of scans, which I will touch on later, and that will maximize your data collection. Its approximate cost is $12,000. And if you look at this image on the left, there's this arm coming up from the center, and that is where external GPS attachments that are compatible with the instrument can be placed. They're directly above the sensor. So the external GPS system that we used is the Juniper Systems Geode GNS3 GPS receiver. Now, this is compatible with a wide range of equipment, and it can connect to iPhones, Androids, or PC, and it utilizes GNSS, or Global Navigation Satellite System, data for sub-meter locational accuracy. So a lot of GPR systems will come with an internal GPS, but that's not going to be as accurate as something like this. So this costs about $5,100. And this is incredibly useful when you're preparing or collecting data that could be submitted to a court of law. You really want that accuracy and precision. So I mentioned there are multiple types of scans, so let's touch on what that looks like and how those work. So your first scan that you'll see is a line scan. So line scan outputs display a cross section of the area that you're scanning. So if we're looking at this line scan here, our x-axis along the top, that's going to be the position or distance walked with the instrument. So you can imagine that as like the surface of whatever you're scanning. And then our y-axis is going to be the depth. So when you're scanning with a geophysical instrument like ours, it's going to be sending waves forwards and backwards as you're scanning, kind of in a V shape. So what you'll see when you have subsurface objects is this hyperbolic, parabolic artifact within your scan. And we see some of that right here. So that's what it's going to look like, but it's pretty non-discriminatory in shape because of the way the waves are interacting. They're going to more or less form some type of parabolic shape. So what you can then do is you can do grid scans. There we go. So grid scans combine several line scans in a grid in order to show reflectance at various depths. So reflectance, what I'm referring to there, is I mentioned waves travel at different speeds and interact with different materials in different ways. So when the waves hit certain materials, they'll reflect and they'll travel slower. So what you'll have in a grid scan is you'll have in your x-axis, direction 1, and then in your y-axis, you'll have the perpendicular direction 2 of your line scans. And then your z-axis will be your depth. So you'll be able to see slices of your scan at different depths, and the grid scan will highlight high reflectance areas. So a lot of people, when they see this color scheme, they think it's temperature, they think it's heat. And I get that, but it's not. Essentially what we're looking at here in this red zone within our grid scan is an area of high reflectance. In this area, the waves traveled significantly different. So the grid scan highlighted that area. So one fantastic thing about this is you have a live output. You can see what you're viewing or scanning while you're scanning it. So what we're seeing here on the right is a line scan in progress. So at the bottom, you see that little blue bar, and this is especially useful. That little blue bar shows you how optimal your scanning is. So if you happen to go too fast, or you lose traction on your control wheel that helps you measure your distance, it'll light up light blue in that dark blue bar, and you'll be able to see that the quality of your scan has dropped in that location, so you can rescan over that area. And by seeing your scans while on scene, you're able to make on-scene determinations on site using subsurface visualization. Additionally, if you want to process data in post, you can use the Echo project software. This is the software compatible with the LMX 200. We specifically used version 6, and this allows for post-scene extraction and processing of collected data. So what are you going to get from that? So Echo project combined with our external GPS will give you 3 primary outputs. You'll have satellite imagery. You can integrate your GPS and GPR data to allow the visual overlay of your scans at the exact location that they were scanned. Additionally, you can do what is called an interpretation on the scene. So let's say you're doing a line scan and you see a target, you see an area of interest. You can flag that in your scan, and then the Echo software will give you the exact position, the depth, the calibration settings, the coordinates, all the information that it collected in regards to that specific flagged location. And lastly, you can look at all the data that you collected within your scan. So I keep mentioning how waves travel. I keep mentioning dielectric or reflectance. So what I'm actually referring to is the dielectric constant of a material. This is also referred to as the letter K. So the dielectric constant of a material is a ratio. It refers to the permittivity of a substrate compared to the permittivity of a vacuum. So the higher the dielectric constant, the slower the waves will travel through that substance. So for example, the dielectric constant of air is 1. It's a 1-to-1 ratio. The radar travels very easily through air. Dry sand has a dielectric constant or K value of 5. Dry concrete, 6.25. And now I'm specifying dry because water can severely impact your scan. So the two main areas that I see when scanning in the field that cause interference or difficulties are water and metal, and this is due to their high dielectric constants. So water has a dielectric constant of 80. That is very high. So what you'll see with water, if you're scanning in an area that's very wet, you'll see decreased signal strength and you'll see increased noise. So what that looks like on our left here is all this TV static that we're seeing in this scan. From about halfway down to the bottom, we're not really getting a read because the soil or whatever substrate this is too wet. Metal, on the other hand, has an infinite dielectric constant. No waves can penetrate metal. So what you'll get are one of two different types of artifacts in your scan. The one we're looking at here is a ringing target. So essentially, metal is there, but the signal is so strong that it goes and reverberates through your entire scan. You cannot tell what depth the metal is located. Additionally, if you're scanning objects like rebar or concrete with rebar, you could see shadow zones where you can see the rebar. It's not a ringing target, but you can't see things immediately underneath the rebar. It's just blanked out. So for our research, we combined GPR and LiDAR to detect simulated graves. So on November 9th, 2023, 2 pigs weighing approximately 150 pounds each were delivered to the GMU Forensic Science Research and Training Laboratory. You all may have heard of this. We also call it our body farm. A team of student volunteers was utilized to dig a grave using common tools to simulate clandestine grave conditions. One pig was buried while the other was placed on the surface of the ground nearby and covered with sticks and leaves. So this is our simulated grave, which is what I'll be focusing on because that's what you can detect with GPR. So on the left here, we have myself, and just out of frame is our volunteers, and we used common tools that you would see in the digging of an unmarked grave. So we had pickaxes, digging sticks, and shovels. And on the right here, this is after the pig has been buried. So as you can see, there's no foliage on the ground really, but other than that, there's no huge indentation or anything. There's no immediate indicator that there is absolutely something buried here. So following the placement of the pigs in our body farm, we completed frequent GPR and LiDAR scanning to observe surface and subsurface changes and decomposition over the course of several months. Following this time period, the data was analyzed to determine the advantages and disadvantages of both techniques so as to better apply this technology to law enforcement investigations. Additionally, we looked at investigating the potential integration of GPR and LiDAR technology for improved grave detection. So I do want to note, we did see scavenger activity, which was very fascinating. So starting about early January, some animals dug about a 4-inch hole directly to our buried pig. And so this was really fascinating because we could see we have really high clay content soil here, and it was winter. It's very wet, it's very cold. It essentially acted as a refrigerator for this buried pig. It didn't really decompose at a fast rate. So we actually got to observe decomposition over time as these scavengers continued to dig at this pig. So to summarize the GPR results that we obtained, as I mentioned, we have high clay content soil, and due to the winter conditions, there was a lot of water present. So scans showed high variability within the grid scans specifically, despite minimal decomposition of the pig up until the very end. Line scans, however, showed lower variability when compared to the grid scans. So our most optimal data outputs directly correlated to low water content of the soil. And we found that issues related to moisture could be mitigated by looking holistically at both the grid scans and line scans when collected under suboptimal conditions. So this is our baseline scan. This is what it looked like before we buried the pig, before we dug any hole. We're seeing a little bit of like maybe some rocks, maybe some uneven surface, but no huge targets, no huge subsurface artifacts. So this is our immediate post-burial scan. So this is in the perpendicular direction. And what that means is this is what it looked like when you crossed over the pig grave over its torso, across its torso. So you're crossing perpendicular to your target. and this created a very clear parabolic hyperbolic target. Additionally, when crossing parallel with the pig, essentially from the head to the tail, we also had a very strong signal. Because you're crossing it lengthwise, you're not really seeing as strong of a parabolic signal, but you are seeing a signal, and this is what it looked like. So this was our most optimal scan, and this is what it looked like in the field on our screen. So what you are seeing here on the left is you're seeing a very strong signal in your line scan. And this line scan corresponds to the arrow that is highlighted on the grid scan. And within our grid scan, we can see there's only one real target in our grid scan. There's one real large area of interest. This is very optimal. We aren't really unsure about what's happening here. We can see exactly where this pig is. So this is what the grid scans looked like. These are each about a month apart. And as time continued and the ground got wetter, we were seeing lots of areas of reflectance. So grid scans don't just show you subsurface structure, they're showing areas of reflectance. So if your ground is saturated with water, you're going to have your grid scan light up, and that can cause issues with interpretation. However, like I said, our line scans were much more promising. So over time, we did see the soil was more compact, especially as I continued to go over it with this heavy instrument, but we could still see very clear hyperbolic targets within our line scans. So earlier I mentioned that water can cause some issues with your scanning. So this is what we were seeing in action. On the left here, this is these scans are about 1 month apart. We see a very large signal for our buried pig, and we see some noise at the bottom, but not a lot. On the right, this was 1 week later after some rainfall, and not only are we seeing a very significant increase in the noise, but our signal for our pig has decreased. It's much smaller, even though we know now it hadn't decomposed almost at all, and this was very early on in the entire process. So our worst scans were areas directly after rainfall and snowfall. And if you're looking for something directly below the surface, this is going to cause some issues for you because, you know, the top few inches to about a foot get really saturated when there's been heavy snowfall or rainfall. So our worst scan here on the right was after heavy snowfall and after it had melted. And what we're seeing is almost the entire grid scan lineup because the soil is so saturated. So what we can consider when going into crime scenes, when looking at law enforcement investigations, is using a variety of tools to mitigate these challenges while still using the GPR. So you could use soil probes to determine if you actually have a subsurface target or if you're looking at water interference. You could use metal detectors when facing artifacts such as those ringing targets. It can indicate if the metal is right below the surface or not. Lastly, cadaver dogs are very useful, but if you're working cold cases, which is very common with GPR, the cadaver dogs might hone in on a specific area rather than an exact spot. So all of these tools can be used holistically to maximize your detection of unmarked graves. So now I will be turning it over to my colleague, Divya, to discuss the LiDAR aspect.
Good afternoon, everyone. This is Divya Rupini Amarthaluri. I'm currently a Mason's graduate student majoring in forensic science. I'm a certified drone pilot, and I'm also one of the grant participants. So an ISA grant funded this research project, and this research project consists of two main components, and that is unmanned aerial vehicle and also light detection and ranging, which is LiDAR. So before actually going into this research project, telling you about the research project, let me give you all a brief overview about each of these components. So coming to the unmanned aerial vehicles, these are also called as drones. These are an adaptable technology whose usefulness is increasingly manifested as many modern day applications are explored. So now coming to the forensic applications of UAV, they are used in traffic accident reconstruction, crime scene documentation, forensic mapping and documentation, disaster victim identification, and cold case identification. So for crime scene documentation and traffic accident reconstruction, drones serve as a valuable tool for aerial photography, especially for gathering information from wide areas, providing a cost-effective alternative to the traditional techniques, which is documenting the crime scene manually. So this method is also time efficient for obtaining high resolution document output. So now coming to the actual UAV that was used for this research project, that is DJI Matrix 300 RTK. It is a powerful industrial drone, which is equipped with an advanced flight control system and a 6-directional sensing and positioning system, which means that it can sense all the 4 directions, including the top and bottom. And it has a 55-minute flight time, allowing extended missions without frequent battery swaps. It also is equipped with an obstacle avoidance system, so it can detect and avoid obstacles without crashing into them during its flight path. So now coming to the second component of the research project, that is LiDAR. So LiDAR, which stands for light detection and ranging. So the basic principle that is involved in the working of LiDAR is it uses pulsated lasers, which is a remote sensing technology to generate a 3D model of an environment. So what is pulsated lasers? So these are just like the regular lasers, but instead of emitting a continuous beam of light, they emit short bursts of light. Like, for example, imagine a flashlight blinking on and off rapidly instead of just staying on constantly. So these lasers, when they bounce back into the LiDAR, they are detected with the help of a LiDAR sensor. So what is a LiDAR sensor? A LiDAR sensor is made up of transmitter, receiver, and detector. Along with this, there is global positioning system and also inertial measurement unit. So there are multiple uses of LiDAR, including mapping and surveying, environmental monitoring, detection and documentation of archaeological sites, and etc. And there are different types of LiDARs, like airborne LiDAR, topographic LiDAR, bathymetric, terrestrial, mobile, and photon counting LiDAR. So the particular LiDAR that was used for this research project is Zenmu's L1 LiDAR, which is an airborne LiDAR. So some of the features of L1 LiDAR is L1 works with RTK meaning real-time kinematics. So the LiDAR requires the RTK services completely throughout the flight time, and I'm going to talk about the RTK in the further slides. So with L1, real-time color point cloud generation is possible. It just means that it has the ability to generate a point cloud in color. And it has 3 returns, which means when the drone is flying, for every 1 pulse that comes out of the LiDAR sensor, we can get up to 3 returns back into the LiDAR. So the L1 LiDAR, it has the ability to perform under low light conditions and heavy foliage. It also has the ability to capture and generate point clouds up to 480,000 points per second, which just means that it has the ability to capture and process these 480,000 individual points in the environment every second. And the price range for this LiDAR, it goes from $7,000 to $9,000. So some of the important features of the L1 LiDAR are inertial measurement unit, complementary metal oxide semiconductor, which is attached on a 3-axis stabilized gimbal. On your right-hand side, you can see the LiDAR, which is mounted on a drone. So IMU, which stands for Inertial Measurement Unit, it continuously tracks the LiDAR's movement and orientation in order to accurately determine the position of the LiDAR. Now, this is done by using a combination of sensors such as accelerometer, gyroscope, and sometimes a magnetometer. Now, coming to the complementary metal oxide semiconductor, which is also called a CMOS, it is a digital camera that utilizes the CMOS image sensor technology to capture images or videos. So the sensor is made up of tiny light-sensitive cells that can turn light into electric signals. So that is, when you take a photo with a CMOS camera, the sensor captures the light coming through the lens and then turns it into a digital picture. So it is advantageous to use this camera because it uses low power and it is also affordable. And lastly, this camera is a 20 megapixel camera. And coming to 3-axis stabilized gimbal, this is useful when there is a pitch, yaw, and a roll. So pitch meaning moving forward or backward, yaw meaning rotating 180 degrees or 360 degrees, and roll meaning moving left or right in terms of UAV. So this gimbal, it helps in obtaining a stabilized footage. So the gimbal ensures that the camera remains steady when the UAV is moving. So now coming to the other important component for the functioning of LiDAR is RTK. So RTK is nothing but, again, real-time kinematics. Before I tell you how it impacts LiDAR, let me tell you how RTK works. So RTK has two receivers. One is a base station, and the other one is a rover. So what base station does is it communicates with the satellites in the sky by using the GPS signal, and then it sends this corrected positional data to the rover. So in here, rover is nothing but the UAV. So it collects the signals from the satellites and then sends the corrected positional data onto the UAV, which is the rover. So when a LiDAR is set on a mapping mission, you want that LiDAR to fly as tight as possible, and you want it to be on all the 3 axes, which is the X, Y, and Z. So Z meaning the altitude. So RTK helps LiDAR to run in these 3 axes. And now coming to the actual research project. So the purpose of this research project was to assess the efficacy of the LiDAR in detecting soil disturbances on unmarked gravesites. So some of the literature review was done prior to implementing the research project, just to know the abilities of the LiDAR mounted on a UAV. So the sensor. An aerial vehicle, Wolpert Cessna, I'm sorry if I'm pronouncing it wrong. So this aircraft, which had a dual head dragon eye sensor LiDAR mounted on it, this was useful in surveying of Malheur County, Oregon. And this sensor, it has a capacity of, or a pulse rate frequency of 1 MHz, which means that it can give up to 1 million pulses per second. So when compared to L1, L1 gives only up to 480,000 points per second, but in here, this LiDAR, it gives you up to 1 million points per second, which means that you're collecting more data, you're getting more data. So hence the surveying of that county was possible. And also the next one was RTEGL VQ 1560i. It is an airborne LiDAR. Now, this also has a capacity or a pulse rate of 1 MHz, which means that it can give you 1 million, up to 1 million pulses per second. Hence, this was useful in a rapid identification of the invasive species, Aguinondo in riparian forest, which is at Warsaw, Poland. So just as Jordan explained you how the research project took place, so you can see the picture on your farther left-hand side of your screen. There is no block. We selected an area where there is no blockage of the tree canopy, since LiDAR has only 3 returns, so we didn't want any kind of hindrance for our scan. So hence we chose a study area where there is no blockage of the tree canopy. And then the rest 2 pictures, it just shows you where the pigs were placed on top of the ground and where it was buried. This was before placing the pigs, and this is after placing the pigs. Again, just as my colleague Jordan mentioned, after placing the pigs in their respective areas, fallen leaves and branches were placed on top of both the locations, just to stimulate a concealment, which is typically seen with clandestine gravesites. So now these pictures, these are just to show you a bird's eye view of the study area. And this was post placement of the pig carcasses. And this was taken by the CMOS camera, which is in the LiDAR. After mounting the LiDAR onto the DJI M300 RTK, it was set on a mapping mission over the study area by using the DJI Pilot app on the controller. So multiple scans were performed post placement of the pig carcasses, and all the scans that were collected by the LiDAR was collected in the SD card. So this SD card was the data from the SD card was transferred onto a computer which has a DJI Terra Software Pro. So this DJI Terra Software Pro, this software is useful for analyzing the data, the raw data that was collected by the L1. So so the version that we used was DJI Terra Pro version 3.6.6. So the raw data which was captured by the L1, it is converted into a 3D point cloud by using the software. So now we're going to look at the 3D point cloud that was generated by the raw data. Now what you're looking at is the 3D view of the Forensic Science Research Training Laboratory. Now what you're looking at is the RGB, which means red, blue, and green. So these are combined in various ways. These are a color module which combines in various ways to produce a wide array of colors. So that is what RGB means. So what you're looking at right now is the RGB view of the 3D point cloud. And the next one, now we are zooming on to the study area. Again, this data is seen in the RGB view. And in the next video, the change of the view is done. It was done by rotating the point cloud. And now, as you can see again, this is in the RGB. This shows the point cloud in the true color form. And moving on, this is the reflectivity. So this is just showing how the light emitted by the scanner and how it interacts with the Earth's surface. So this is the reflectivity view of the 3D point cloud. And moving on to the height. Now this shows the elevation changes across the site, highlighting the higher and the lower points of the data set. And then next, we can view this in returns too. So this displays a number of returns. Yes, sorry. Yeah, so this is the returns view. So this displays the number of returns that were recorded by the L1 sensor. And yes, sorry. All right. So now coming to the results. So the L1 LiDAR was chosen for this project because it was economically feasible for public safety organizations when compared to a higher end LiDAR, which are expensive. So after thorough analysis of the data, the soil disturbances were not visually distinguished, and that was the observation that was made. And the key aspect that should be noted down and highlighted about the LiDAR is its connectivity and its data acquisition. It's easy for it to get connected and also to acquire the data. But however, with these advantages, there are some drawbacks, and that is the quality of the data collected. So this is the quality report that you get after you process the data in the DJI Terra Pro software. And this just gives you an overview on what input data was and what was the parameters. And the overall impression of this L1 LiDAR in terms of finding disturbances on the soil at the Clandestine gravesites is it is efficient in data acquisition, and it is also easily deployed into the field. But however, the quality of the data obtained in this project was lacking with regards to the details of the post-process results. So now that I've talked about L1, let me give you all a brief overview on L2 LiDAR. So this is L2 Xenius LiDAR. So since L2 has been recently released into the market, we believe that L2 has more capability, and it is also more expensive than L1, but it is still within the range where public safety can afford. So L2, sorry. Yes. So L2, it can penetrate vegetation deeper to get more ground points with increased returns, which what that means that L2 has 5 returns, whereas L1 has only 3 returns. So with 5 returns, L2 can penetrate the canopy and can obtain the ground points. So it can penetrate and also returns that we get. So we are getting more ground points too. And also L2 has more accuracy or higher accuracy. Like for example, it gives an accuracy of 2 centimeters at a distance of 150 meters, whereas L1 it gives an accuracy of 3 centimeters at a distance of 100 meters. And L2, it can cover more area. It can cover up to 2.5 kilometers square in a single flight, whereas L1 can cover only up to 2 kilometers square per single flight. And L2 has the ability to capture and generate point clouds up to 1.2 million points per second. Again, when compared that with the up to 48,000 points per second from L1, this gives you more amount of points, which means that you're collecting more amount of data. And the survey speed. So L1 requires 5-minute warm up period for the IMU to stabilize and calibrate, whereas for L2 it is ready to fly. So L1 it requires the warm up period before flying, but whereas L2 it is ready to fly. And now coming to the positive attributes of the LiDAR mounted UAV is, first of all, it is easy to use and it can map a large area within a stipulated time, and real-time data acquisition can be obtained. Also, additionally, the higher end the LiDAR is, the detailed analysis of the data that you can obtain, and also archaeological discovery, soil erosion detection, landslide detection, and also geomorphological detection can be obtained by using this LiDAR mounted UAV. And some of the disadvantages or drawbacks of the LiDAR mounted UAV is the flight time and battery life. Like for example, let's say your UAV or your drone flies out of battery midway of the mapping mission. So you have to stop that, get the UAV back on the site and then switch the batteries. So that's one of the drawbacks, and also the environmental factors. You can't fly a LiDAR mounted UAV in when it is raining, or when the wind gusts are high, or when it is snowing. So these are some of the drawbacks of the LiDAR mounted UAV. And further research on this present research, what I wanted was use of high resolution LiDAR. Just as I told you, the higher the resolution of the LiDAR is, the more amount of points that you're getting, which means that the more amount of data that you're collecting. So which means that it gets easy for us to distinguish the soil disturbances. And also this research can be more significant by using the human remains instead of animal carcasses. And additionally, the collection of data for an extended period of time, since we were time crunched, I wanted to know what kind of results that we could get if this research project can extend for more time. And yep, just as I have mentioned in the beginning, this research was fully funded by NIJ grant. All the materials were purchased by using the funds from the NIJ grant, and also the research area, just as my colleague Jordan mentioned, this research area was done at GMU SciTech campus, Forensic Science Research Training Laboratory. And that is it. Thank you.
Okay. So greetings, folks. I guess you can turn off the slides.
Okay.
Great. All righty. Welcome. My name is Steve Burmeister, and I'm from the George Mason University's Forensic Science program. I believe that, as we can all see, that locating and finding a clandestine gravesite is extremely challenging, especially when given little to no intelligence on its location, which is oftentimes the case that we have. Public safety organizations may get intelligence as to the location of a particular site, but usually it's general in nature, and the information is vague, and the site location is rather large. This can also be hindered by other obstacles, such as a vast terrain and extensive foliage. Thanks to unique technologies such as GPR and LiDAR, we are moving one step closer to finding a solution to this challenge. Now, with that being said, no one piece of technology or capability will solve this problem, but rather a combination or layered approach may well be the answer. Our particular strategy from the beginning has been really a from the ground up approach. And in other words, we're looking from underground all the way to the air. I think we've demonstrated through the GPR that anomalies under the ground can certainly be isolated. We also showed that the LiDAR can indicate, despite trees and other terrain obstacles, the surface topography, and that can be studied while flying overhead. But as previously stated, each of these technologies by itself cannot locate a gravesite if we're trying to find it in a vast area with no information. So the next approach is to examine other technologies, such as multispectral sensors, which can be flown from overhead. Hopefully, these will provide another piece to the puzzle to direct investigators to potential locations. Our hope is that by coupling this information, or in other words, layering it, we will be able to narrow down the search area from multiple acres, perhaps now to feet. We will also explore utilizing techniques such as artificial intelligence to rapidly examine and identify anomalies encountered by each technology in the layered approach. A critical aspect to accomplishing this by identifying the actual location is by knowing the anomaly's geolocation as it is on Earth. This allows technology to be stacked and to overlaid on one another. So, in other words, the system can then bring these anomalies together to better isolate a target location. To get there, we obviously have to train the systems on what to look for when exploring the data. Technology systems such as GPR and LiDAR bring us one step closer to this reality, so I think we are very close to solving this everlasting problem. So I'd like to say thank you to everybody that has listened so far. And I'm going to turn the presentation over to our moderator, who will see if you have any questions for any of us.
Hello, yes, thank you. My name is Erica Christensen. I'm a forensic scientist with RTI International. Thank you all for such a great and informative presentation. We do have some questions kind of filtering into the chat, so we will move towards those. The first one, it seems, is related to GPR. So this one's for you, Jordan. Were your grid scans plotted with the exact same gain?
So while we were doing the grid scans, we did use the same gain. However, we did change the soil calibration. So for those of you unfamiliar with GPR usage, you can calibrate your soil calibration depending on how much moisture, because like I said, moisture, water in whatever substrate you're scanning can really have an effect on what you see. So while we did keep the same gain, it was a setting of 4, I believe. We did adjust the soil calibration for those much wetter days versus the drier days. But we really wanted to keep as much of the parameters identical as possible. So we did mark the barriers, about a 10-foot plot, 10-foot by 10-foot plot around the grave with flags, and we used measuring tapes every time we were out there. We didn't want to mark it up with like spray paint, as you might see with utilities, because we didn't want to interfere as much with the LiDAR scanning visually. But we used measuring tapes and these permanent flags to ensure that we made the same lines every single time, and we kept as much of the settings the same as possible.
Excellent, thank you. Look, the next couple are for Divya. They're related to the drone. So the first one is, what altitude did you fly the drone? And can you give any details about your flight specs or flaps?
So we flew the drone 150 feet above the ground level, and the specs would be the L1 has 450 meters range. So
Excellent, thank you. And
sorry.
then, oh, that's okay. The next one, what is the resolution for the LiDAR? Either both versions that you utilized.
The resolution was 1280 by 960 for the L1 LiDAR.
Wonderful. And then there was another question related to the functional differences in the frequencies of the L1 scanner versus the L2 scanner. So could you go into those differences a little bit more?
Yes, as I mentioned before, the L1 has the points up to 480,000 points per second, whereas for L2 you have up to 1.2 million points per second, which means that you're getting more data with the L2 when compared to the L1.
Excellent. Thank you for that. And then, Jordan, this one's for you. Why does the GPR scan appear like an infrared scan?
That's a great question because, as I mentioned, a lot of people see that color scheme. They see the reds contrasted with the blues and kind of the yellow greenish fringe, and they immediately think temperature. So the reason why this color palette is typically used is because it shows high contrast with those areas. The red is very easily distinguishable from the blue. However, this isn't the only color palette available. There are several options within our instrumentation. This is just standard because it's so easily distinguishable in those target areas of high reflectance.
Excellent. Thank you for that explanation. And then it asks, did you process the image collections with ArcGIS Pro?
So I did not personally use that software, although I have heard of it. Our previous anthropologist did utilize ArcGIS Pro. However, because we had the Echo project software, that is the software specifically compatible with the LMX 200. So that's what we utilized for this project.
Excellent. And then this one is a little bit more related to the criminal investigation side. So has the LiDAR with drones been used in court at all? Have there been any Daubert hearings that you know of involving them, their usage?
I'm going to throw in, I'm not aware of a actual Daubert hearing yet using LiDAR. A lot of use with UAVs or drones is slowly finding its way into courtrooms. And obviously, most of those entries into courtrooms have involved the use of just visual cameras or perhaps a thermal camera. The next level of sensor is obviously to move to get LiDARs into a courtroom. And my knowledge is that I'm not aware of a particular case that has actually been adjudicated using a LiDAR detector. That does not preclude there may be civil cases that are out there, but I'm looking at it from criminal cases. I'm not aware of a criminal cases. There may be civil cases where runoff or woods have been inspected using a LiDAR. So from a criminal side, I'd say no. We have to look towards that as the next future problem because Dauberts are definitely one area that we have to be aware of, and we'll see as any technology enters into court, such as LiDAR. So, and that goes for GPR as well.
And one question was, did you guys consider using terrestrial LiDAR first before moving to the UAV incorporation? Or I guess what was your decision process there? And the audience member references, Kokorin et al. Of 2018, an article.
Yeah, let me jump in. Jordan, you can weigh in at any point on this, but the advantage is there's no question that terrestrial-based LiDAR is a fantastic tool. You're limited, though, in the scope of the area that you're working with. And I think the problem set that we were looking at is public safety is oftentimes posed with a problem. Go to this vast wooded area and find where the body has been buried. Or you have intelligence from a gang member who said, I buried it up on that hill. Well, the hill may have several hills. And so in order to cover all those hills would take it would take an extreme amount of time. So the scope and theory behind using the LiDAR from an aerial platform is covering a vast area. And when I say layered approach, we may very well come back in with a terrestrial LiDAR when we've isolated a particular spot. So in other words, it's sort of the term person of interest. We've all heard of that. This is a object or location of interest. So now we can focus on that area. And now once we've got that focal area, we can come in with these other technologies. But to find that one spot that we should all be staring at is the challenge. And that's when terrestrial LiDAR can come in, GPR can come in, and other sensor packages that are still yet to be discovered that can come in and really find our exact location. But our problem sets are typically go out and look in these woods for something, and you may be spending days and days and days if you were down on the ground trying to find it. So that was our approach. That was our theory from the beginning, is how do we use a technology to cover a vast amount of space.
So like an initial kind of filtering, look big first, and then kind of move down as you get more information.
Right, and you probably are sitting going, well, this person just said he works from the ground up, but our project was working from the ground up, but yet using the top to explore virtually down. So our goal is to cover a large area, isolate the important spots, and then come in with heavier equipment, so to speak, and find and refine that location. Yep.
Excellent. Thank you for that. Jordan, a little back to the GPR. When utilizing the equipment, how quick or slow do you need to move? Do you have any tips and tricks for running the machinery?
So it's really great because, as I mentioned, it has that little blue bar as you're scanning line scans that lets you know if you're going too fast, if you're decreasing the quality of your scan. I would liken the correct speed. I can't give you an exact metric unit, but it's like mowing a lawn. So you're not running and sprinting when mowing a lawn, but you're also not going super slow. You just want to maintain a steady pace.
Excellent. Thank you for that. And in regards to that, a couple attendees ask, how would the either the ground being frozen, presence of permafrost, or any large roots underground, how would that kind of affect the GPR? And does it still work when that ground is frozen?
Absolutely. So I'm going to address this in two different parts because you're going to see differences with the roots compared to the frost. So as I mentioned, water has a massively high dielectric constant. Surprisingly, though, ice does not. And so the reason why water interferes so much with GPR is because water is polar. It's partially positively charged and partially negatively charged. But when water is in the form of ice, it sits in a lattice that kind of neutralizes isn't the right word because that's going into charges, but it helps order the water in a way that doesn't interfere as much with the polarity of the waves. And so you can actually scan on ice much better than you can scan on wet ground. I actually believe that that was one of the primary historical uses of GPR. It was invented back around the 1930s, and they were actually using it to measure glacier depth. So you can actually get some pretty good outputs even on frozen ground. Now, roots, on the other hand, that is an object that is below ground. So if you're scanning and looking for an object below ground and there are roots, especially sizable roots, you're going to see that. So as we saw from these scans, these aren't like x-rays. You're not seeing super high definition, high quality, picturesque representations of what's below the ground. It really takes a lot of experience to be able to look at all the scans that you've collected and say, okay, this I think is a tree root, but this could be a femur. So it's all about experience, looking at what you have, taking what you possibly know about the area, the terrain. I like looking into the soil composition before I go to a location, because essentially you're not getting an x-ray of the ground. This is very different. It would be nice to get an x-ray of the ground and go definitively right here, that's a root, but this is a skull, but that's not the case. So you just really need to take a broad approach and keep your mind open because, you know, sometimes a stick is just a stick. It's not a bone. It's not anything of interest. And it's hard to distinguish between that, which is why the LiDAR aspect of this could be incredibly useful if we could hone in on anomalies that could potentially indicate the location of clandestine graves. Because if we're looking at, for example, a heavily wooded area deep in the woods, we got a tip that someone was buried there, but it was a long time ago, so there's not going to be much left. It's going to be very hard to distinguish between bones and a large rock, for example. You have to be able to use your experience to determine that. So then if LiDAR could come in and identify this area looks like an anomaly, this might be an unmarked grave, that could significantly increase your chances to interpret the area.
Excellent. Thank you for that. We're getting close. A couple more questions. One is if their agency is considering purchasing either GPR or LiDAR with a drone, Are you aware of any published standards, or I guess where did you guys kind of start your journey when they were looking to develop your own standards?
That's a wonderful question, and I think you're falling into my stacked corner here, because one of the project goals here is to actually establish a set of standards and guidelines for public safety organizations. The quick answer to you is there are no guidelines right now. And that's where we hope to go with this, is to offer some guidance, and it will be through RTI's program that we'll be able to provide that to the listeners on here and to others through your portal and other sources. So a short answer to your question, there's no guidelines that are out there now. We intend to establish those guidelines and help guide organizations, because it is a difficult question.
Absolutely. And then one more. So this viewer says GPR has been in the media a lot in Canada to find graves at residential schools. Can you comment on whether you'd get clearer signals from skeletons only versus the carcass with flesh, or what differences do you anticipate?
So I actually have a bit of experience, kind of tangential to what they're referring to in Canada. So what they've discovered in Canada is that many residential schools have mass unmarked graves or cemeteries from children who passed away after being sent to these residential schools. Here in Virginia, I actually worked with some archaeologists and anthropologists because we had a series of unmarked cemeteries detected by archaeologists in a nature preserve. So it was actually very similar. But what you'll see essentially with our large geophysical instruments is that the bigger the target, the easier it is to detect. So something with flesh is just going to be a bigger target, and it's probably going to interact with the waves more because, at that point, there's still some fluids involved. So that's going to be easier to detect. But additionally, what I've noticed both in reading literature about these residential schools and their mass graves, as well as the unmarked cemeteries we worked on, is there are often times where there are coffins involved. I've done multiple cases, both criminal and non-criminal, that involved coffins. So you're not actually looking for a body itself, you're looking for a box of some sort. And so the bottom line is the bigger the target, the better, but you never know what to anticipate when you go out there.
Excellent. And then kind of as we wrap up, I do apologize for the questions we couldn't get to. The presenter's information will pop up at the end. But the last one we'll answer live today. Many of our viewers were very impressed by your scans, your work, and they wondered, do you guys provide kind of assistance to local law enforcement agencies to kind of come out and utilize this equipment on scenes?
Well, I'll answer that. We have certainly assisted other organizations and agencies with work. Jordan is a perfect example of that. She's attending George Mason, soon to go to her graduate program, but she has gone out on actual cases, and she's been cleared by our police department to be involved in these cases. So yes, the short answer, if people make a legitimate request and it goes through the normal channels, which you can make it through either the forensic science program or through the GMU police department, yes, we can assist with that help for any type of a casework. But it has been done in the past, so yes.
Wonderful. Well, like I said, the viewers were very impressed by the scan data as well as the results that you guys were able to produce. We're so thankful for you all for this great presentation and conversation. And as I mentioned, our presenter's contact information is on the screen now, if you'd like to reach out to them to address any of the questions or comments that we did not get to today. So thank you all and have a wonderful day.
As you depart, we kindly ask that you take a minute or two to complete our post-event questionnaire. The link will be pasted in the chat and also appear as you exit the Zoom room. Your feedback helps us improve our outreach efforts and continue to provide the best experience possible. Thank you again for attending, and we hope everyone has a great day.